Propanone reacts with bromine in alkaline conditions. The rate equation for this reaction is rate equals the rate constant K times the concentration of propanone times the concentration of hydroxide ions. Sketch a graph on the axes provided to show how, at constant temperature, the concentration of bromine changes during this reaction. Now this question did have a few problems in the exam because there wasn't enough information to make an absolute certain decision on which graph to draw. The exam board wanted for you to just draw how concentration changes over time for a reactant. So actually all they wanted to see was a curve of decreasing gradient. Okay, so that's all they wanted to see. What the problem was is this is the curve that's true when all the concentrations are maybe similar, but students could have misinterpreted this question and looked at the rate equation, and when you look at the rate equation and you see that bromine's not there and bromine's zero order, you may be tempted to draw the graph that shows zero order, and the graph that shows zero order is a straight line decreasing line like this. Now the exam board said that because this is only true if all the other reagents are in large excess, this isn't what they wanted, but given that the amounts of none of the reactants were shown, they had to accept both. So the line that they wanted was the regular reactants decreasing gradient curve that shows how a reactant is used up. Table 1 shows the initial rate of this reaction for experiments using different mixtures. It says complete table 1. So let's just rewrite the rate equation that they gave us. So it was rate equals K times propanone first order and OH minus first order. So the bromine was zero order. There are two ways to do this. You could do the second part of the question first and find the value of the rate constant K by rearranging to say rate K equals rate divided by concentration of propanone times by concentration of hydroxide ions. Put the numbers in. And propanone is 1.5 times 10 to the minus 2. And hydroxide is 2.5 times 10 to the minus 2. You can put that on your calculator. And you're getting 7.33 times 10 to the minus 8. And you can work out the units because you've got the units of rate, moles per decimeter cubed per second, divided by the units of concentration twice. And so if you work that out, you've got moles to the minus 1, dm cubed, seconds to the minus 1, 7.33 times 10 to the minus 8 as our value of K. So what you could do to find the other numbers is you could do it by ratios, or you could use K to find it. So for example, now that you know K, it's quite easy to fill in the bottom line because you can take your value of K, times it by the value of propanone, 3.75 times 10 to the minus 3, and times it by the value for hydroxide, 1 times 10 to the minus 1, and you can get an answer for filling in the table for the rate for experiment 3. That's fairly straightforward to do using your value of K. You could also do these by ratios, so you could have a look at the change. So the first one was 3.75 from 1.5. So 3.75 times 10 to the minus 3 over 1.5 times 10 to the minus 2. And so this change is a quarter. and we're ignoring whatever happens to bromine because it's zero order. And then the other change, so if you do the other one, 1 times 10 to the minus 1 divided by 2.5 times 10 to the minus 2, that's times 4. And as they're both first order, these two effects cancel out. So with times in by a quarter and then times in by 4, it becomes the same number, which is why the value for the rate is the same in experiment 3. So you could do it either way. To find the value for OH minus, you could rearrange the rate equation to say OH minus concentration is rate divided by K times propanone. So what we're doing is we're taking numbers over from the original rate equation, and then we're going to sub in the values. So 8.25 times 10 to the minus 11 divided by our K, 7.33 times 10 to the minus 8, and the propanone concentration in this reaction, 1.5 times 10 to the minus 2. And we should be able to find out what the new concentration is. That's coming out as 0.075, or if you want to keep it consistent with the other numbers, you could write it in standard form, 7.5 times 10 to the minus 2. Figure 1 shows an incomplete mechanism for this reaction. So let's just remind ourselves the rate equation was rate equals K times propanone times OH minus. Complete the mechanism by adding 4 curly arrows and any relevant lone pairs of electrons. So you want to be spotting the difference. So what we can see here is this OH minus becomes H2O by grabbing this hydrogen, but that we're forming a double bond here and we're breaking the double bond here. So we need to make that happen. So this hydrogen that is being fetched by the hydroxide ion is falling off, and it's using its electrons to create the double bond, and then we're going to open the double bond between the C and the O to make an O minus. Then what we want to have a look at on the next thing is how does the next step differ. So we can see that we're making a C double bond O, we're making a CBr, and we're leaving a Br minus. So we're making a C double bond O, we'd have to use a lone pair to reform the double bond, then the CC double bond is collecting a bromine, and we must be breaking the Br-Br bond and putting the electrons onto the Br to make this Br minus. So we've added 4 curly arrows and 1 lone pair, and that has completed the mechanism. Use evidence from the rate equation to explain why step 1 is the rate determining step. So look at the rate equation, it's got 1 propanone and 1 hydroxide, and step 1 has 1 propanone and 1 hydroxide. So step 1 includes 1 propanone and 1 OH minus, and these are the species and orders in the rate equation. Okay, so everything that was in the rate equation is in step 1 in the right quantities.